All right, here we are. We're back here. It's chapter 7, wrapping up the last section. We'll split it in two parts here. We got 7.3. We're going to be talking about sampling means. We got our growth targets of things that we're going to look at, and yeah, some good information putting on here. So let's get into the idea here that the sampling distribution of the mean, of the sample mean, x bar, it describes the distribution of values taken by the sample mean in all possible samples of the same size from the same population. All right, so here's the approximate sampling distribution. Remember we did that pennies example of the ones, the dates on there, if that's of size 5. Then we did this with sample size of size 20. All right, so there's a little less variability, of course, as we mentioned there. So suppose that x bar is the mean of a simple random sample of size n, drawn from a large population with a mean mu and standard deviation sigma. Then the mean x bar is the same as the mean of the population, but then the standard deviation is, we're going to take that population standard deviation and we're going to divide it by the square root of the sample size is what we're going to do. So remember, write those formulas down, have those handy, look at those problems, and again, we're going to look at that 10% condition. We want that sample size to be less than 10% of the entire population. All right, so again, keep that in mind, that again, with replacement, that's what it is. So when we don't do it with replacement, we just have to make sure that that sample size is 10%, or less than 10% of that population, and then it does make it normal. So keep that in mind. Now, AP tip, make sure you're using appropriate symbols. Make sure you're using p hat, x bar, n, p, mu, sigma, all those to make sure. If you're not sure, don't use them incorrectly, but hopefully we get used to those. All right, here's a problem. Number of movies viewed in the last year by students at a large high school has a mean of 19.3, standard deviation of 15.8. Suppose we take a simple random sample of 100 students from the school and we calculate the mean number of movies viewed by members of the sample. Now, what would be the mean of the sampling distribution? Well, as we just talked about, well, it's the same as the mean of the population that we have here. So we'd have 19.3 movies. Now the standard deviation, now we would take the population standard deviation and then we're going to divide that by the square root of the standard deviation. Well, let's refer to that as 10, so 1.58 movies would be that. So again, we want to make sure that simple random sample of size 100, the sample mean number of movies viewed will typically vary by about 1.58 movies from the true mean. Again, that's population mean of 19.3. Let's just double check to make sure our 10% condition's met, and it is, of course. All right. Now we've described the mean and standard deviation of the sampling distribution of a sample mean x bar, but not its shape. That's because the shape of the sample distribution depends on the shape of the population distribution. And what we know is that if the population distribution is normal, well, then so is the sampling distribution. That's kind of a logical conclusion, I would think. And it is true no matter what size the sample size is, so keep that in mind. All right, so when again, just kind of talking about this, remember that suppose that the population is normally distributed, the mean is mu and the standard deviation is sigma, then the sampling distribution of x bar has the normal distribution, it's normal as well, has the same mean, and just the standard deviation is just, you have to take the population standard deviation and divide it by the square root of your sample size, as long as your sample size is less than 10% of your population. All right, so here we go. The heights of young women following normal distribution, mean 64.5 inches and standard deviation 2.5. Find the probability that a randomly selected young woman is taller than 66.5 inches. Okay, so we go in, we want to find our z value, so we take the actual 66.5 minus our mean divided by our standard deviation that we have here, and we're going to get 0.8. Okay, so that kind of gives us that z-score, and then again we can use that table, and then we'll figure that out. We got to subtract that from 1, of course, and get 21.19%. All right, so we got that. Now let's go ahead and let's find our, for B, let's find our mean, of course, would be the same as the population mean, 64.5. Standard deviation this time, of course, we're going to have to take the 2.5, we're going to have to divide that by 10, the square root of 10. And so that's our standard deviation here when we're doing a sample, okay? Now with that, we're trying to look at, because we're going to assume that it's normal because the population is normal, all right? And we also know that 10 is certainly less than 10% of all young women, so that condition's met. So let's go in, let's find here, we have our actual 66.5 minus the mean, but this time our standard deviation of our sampling distribution is going to be 0.79. That gives us a z-score of a 2.53. All right, so of course, what we're seeing over there is we'd have to find that it's bigger than, so we have to take the 1 minus the probability, and we have 0.0057. Okay, so not quite as likely there as we see. All right, so compare the sampling distribution of the sample mean of 10 young women with the population distribution. Now you kind of see the difference there a little bit, is that we're going to get a little bit different curve, a little bit still normal, but just a little bit different. And again, many students lose credit on probability calculations involving X-bar. They forget to divide by the standard deviation by the square root of n. Make sure that you do that. All right, and remember that averages are less variable, so therefore remember that you should be dividing by that. Okay, so keep that in mind as we're going here. All right, a couple more slides here. Let's take a look. Now again, for most population distributions, they're not normal. And here are approximate sampling distributions of X-bar from sample sizes of 2, sample sizes of 25, and 3 different populations. So you can kind of look through all those. You can kind of see what's going on there. So draw a simple random sample of size n from any population with mean of mu and finite standard deviation of sigma. The central limit theorem, we'll call it the CLT, central limit theorem, says that when n is large, when your sample size is large, the sampling distribution of the sample mean is approximately normal. Okay? All right, so there we go. That's going to be the shape. So we're going to know that no matter what the sample size is, okay, it's normal. But if the population distribution is not normal, the sampling distribution will be normal when sample size is large. So what do we say by large? If it's bigger than 30, is kind of the idea. If the sample size is small and the population distribution is not normal, sampling distribution will retain some characteristics of the population like skewness. But if we're getting over 30, we're going to say it's normal. Okay. All right, so here we go. Keith is the manager of an auto care center based on service records from the past year. The time that a technician requires to complete a standard oil change and inspection follows a right-skewed distribution with a mean of 30 minutes and a standard deviation of 20. Now for a promotion, Keith randomly selects 40 current customers and offers them a free oil change inspection if they've redeemed the offer during the next month. Now Keith budgeted an average of 35 minutes per customer for a technician to complete the work. Now will that be enough? Will that work? Well, let's take a look. All right, so the average is going to be 30. That's from our population. All right, so now what we're going to do is, there's 40, so that is bigger than 10% of all current customers. We're assuming, or 40 is less than that. It's less than 10% of all customers. We're going to take the standard deviation is going to be the 20 divided by the square root of 40, so 3.16. Okay, so now what we're looking at here, because the sample size is large, it's bigger than 40, the distribution we can say is approximately normal. All right, so we're going to take the 35 minus the mean of 30 divided by our standard deviation of 3.16. That's 1.58. So anything more than 1.58 is going to be 0.0571. Using that table, take 1 minus that percentage there. Okay, or you can use the technology, of course. All right. So what we're saying here is that there's only a 5.71% probability. Well, we get 5.68 if we do that. Depending on how you round it up, I'm going to say 5.71 probability that Keith hasn't budgeted enough time to complete the work. So I think we're probably okay there. You know, we're looking at that area. We're saying, yeah, we're okay. All right. So looking at this, just looking at some z-scores, if we're trying to say, okay, we want to be 95% or 99% certain he doesn't go over budget. So by using that 0.99, if we go find that on our z-table and find the proper z-score, that ends up being 2.33. So what we have to do is kind of say, okay, what should we budget for time? Well, if we multiply this by 3.16 and then add 30, we're going to see that, yeah, this is going to be 37.4 minutes. So that's what we should probably be budgeting for time to make sure that we have a 99% certainty that we're not going over budget. That'd be important for us to do there. Okay. All right. Well, that takes us care of the first part of Section 7.3 will come back next time and kind of be talking about the difference between two means is what we'll do next time. Okay, until then, I'm Mr. Moon.